Everybody is talking of decarbonization, hydrogen, green hydrogen, etc. And we feel that there is a lot of confusion on the subject. So we are making a small effort to clear the confusion and give the complete insight of a green hydrogen business here. This slide is showing the topics covered in the presentation, like why do we need hydrogen, why do we need green hydrogen, types of hydrogen, why India is betting big on hydrogen, what is the forecast of Niti Aayog, what are the government policies, how the hydrogen is manufactured, what are the opportunities in hydrogen manufacturing sector, the technical review, the storage and transportation of hydrogen, and requirements and recommendations. As we know all, hydrogen is number one element in the periodic table. Although hydrogen is available in abundance, it is not available in free form. It is always combined with some other elements and it needs to be extracted for its use. Hydrogen requires very low amount of air or oxygen to burn. When hydrogen is burned, it produces water vapors, means there is no carbon or greenhouse gas generation during the process. Hydrogen is not a direct substitute for coal, oil and natural gas, but it can help to decarbonize. Hydrogen could account for 12% of global energy by 2050. Decarbonizing the planet is one of the main objectives which world has taken over. The developed countries have agreed for decarbonization by 2050, whereas India has pledged for it by 2070. Decarbonizing the production of hydrogen gives rise to green hydrogen. Means in green hydrogen there is no carbon element involved, either in manufacturing or in usage. Green hydrogen could be a huge value addition opportunity for India as it pivots towards renewables and for imported fossil fuels, which currently meets most of the oil and gas demand in India. The conventional process of making hydrogen use fossil fuel. A novel green method of generating hydrogen could reduce global warming and greenhouse gas generation. Green hydrogen is produced by using renewable energy to split water into hydrogen and oxygen. Hydrogen is a key input materials in fertilizer and refineries, so green hydrogen would help these industries cut aggregate emission. Till now, we have been focusing on renewable energy sources for clean energy, but for industry and transport sector transition to net zero emission, a clean fuel is required, and that clean fuel is green hydrogen. When we use renewable energy for production of hydrogen, there is no carbon or greenhouse gas generation. When this hydrogen is used as a fuel, there is no carbon or greenhouse gas generation as it produces only water vapors and it is the complete green fuel. This green fuel can help minimize the carbon generation and bring down the global warming to the desired level of 1.5 degree Celsius. Hydrogen is a energy dense fuel. Hydrogen has a very high calorific value compared to petrol. It is about 10 times more. Hydrogen has very low density and it is highly inflammable. Hydrogen efficiency to wheel is about 25%, whereas fuel cell efficiency is about 60%. The specific energy of hydrogen is 3 to 4 times higher than gasoline and diesel. Similarly, the specific energy of hydrogen is about 30 to 90 times more than lithium batteries. When we burn petrol or diesel, gasoline emits about 75 to 85 gram of CO2 along with other harmful substances such as nitrogen oxide, hydrocarbons, and particulate matter, whereas hydrogen only emits water vapor as a byproduct. Hydrogen can be blended with natural gas, CNG, LPG, etc., or other fossil fuel in small portion. Hydrogen has the highest energy content by weight of any chemical fuel. It is 3 to 4 times higher than gasoline. Hydrogen is one of the important feedstock for industry as it is widely used for fertilizer and refinery. Hydrogen also powers the fuel cell with no emission. Hydrogen and fuel cell is the best combination for energy requirement as emits only water vapor. Hydrogen is one of the best energy carrier. Hydrogen is used for power generation. Hydrogen is used as synthetic fuel. Hydrogen is used for fuel as a hydrogen vehicle. Hydrogen is used for heating. Hydrogen is used for metal refining, and hydrogen is used for manufacturing ammonia and fertilizer. This is a wide use of hydrogen in industry. Why hydrogen economy is important for India? The one of the main reason we are importing energy worth $160 billion, and the import bills for energy can be minimized with the hydrogen in place. We also have committed for decarbonization by using more and more renewable energy. Currently, we are having installation of 92 gigawatt of renewable energy, whereas by 2030 we want to increase this generation to 450 gigawatt. This is possible with green hydrogen generation. We are one of the third largest carbon emitter after US and China. We are emitting about 3.6 gigaton equivalent of CO2 in the atmosphere. And in order to become a clean energy leader, we need to minimize or zero down this carbon emission, and this is possible with green hydrogen. The energy import bills of 160 billion, which are growing every year and year, consist of crude oil 112 billion, natural gas and LNG approximately $10 billion, coal $23.6 billion, petroleum products $16.2 billion, and ammonia about $775 million. This import bill can be minimized with the green hydrogen if it is in place, and that's one of the main reason why government is focusing on green hydrogen and promoting green hydrogen manufacturing in India as per the recent government policies announced. Green hydrogen manufacturing is going to help us in two goals. One of them is energy security and second is decarbonization. Even if we do the complete decarbonization of our energy generation, that is, if we replace the 100% power generation by green energy, we are going to reduce only 18% of the carbon emission. The balance 82% of carbon emission is coming from other sources which need to be minimized. And for this decarbonization of 82%, we need to concentrate on green hydrogen usage in industry, transport sector and other areas other than energy generation. Hydrogen is a colorless gas. Then why do we say green hydrogen, blue hydrogen, grey hydrogen? It is basically designated from the type it is manufactured. In grey hydrogen, we do the steam or methane reforming, and the energy used is non-renewable energy. So when we are manufacturing this, there is a carbon emission in the atmosphere, and that's the reason it is called grey hydrogen. In blue hydrogen, the steam methane reforming is done and the carbon generated is captured or it is stored. So this carbon generation is not released into the atmosphere, but there is a carbon generation during the process, and that's the reason it is called blue hydrogen. In turquoise hydrogen, methane is pyrolysis and the carbon content generated are stored. The energy is again non-renewable energy, so there is a carbon generation during the process, and this is called turquoise hydrogen. The pink hydrogen is a type where water is electrolyzed with electricity. Electricity is received from the nuclear power. In green hydrogen, water electrolysis is done again, but it is done with the renewable energy and it does not do any carbon generation during the process. Since there is no carbon generation during the manufacturing of the hydrogen, it is called as green hydrogen. And hereafter we will be talking more and more on the green hydrogen because India aims to be a world leader in manufacturing and supply of green hydrogen to green hydrogen is made by electrolysis of water and the energy used for electrolysis is supplied by renewable source. Since the water is split into the hydrogen and oxygen, there is no carbon emission in the process and as such it is termed as a green hydrogen. So in this green hydrogen process, we use the energy which is from renewable energy. This energy is given to electrolyzer. The electrolyzer does the electrolysis of the water. The hydrogen is distributed, stored and further used for end application. During the end application, the exhaust is only water vapor and there is absolutely no carbon generation or greenhouse gas generation in the process, and that is the reason it is called green. This is a schematics of electrolysis process. We have a green energy as a input, we have a water as input. The green energy and water is supplied here in the electrolysis. The electrolyzer convert this water into the hydrogen and oxygen, and this is a basic process of electrolysis. India has the lowest solar energy price at 1.99 rupees per kilowatt. And with this low energy price, India is targeting a green hydrogen price at $1.5 per kg by 2030. With this lowest price, the country is trying to be a global hydrogen supplier and take a lead. Hydrogen can decarbonize the different areas like energy by blending it with natural gas for heavy duty transport and fuel application. Hydrogen can be used as a energy storage also. Hydrogen is used as feedstock in chemicals, in steel manufacturing, for fertilizer and for refining. So hydrogen has a very wide application. Green hydrogen can reduce more than 30% of carbon emission in sectors other than energy. This 30% plus is contributed by chemicals, refining, cement, iron and steel industry, and heavy transport. Current hydrogen demand as on 2020 was 6 million tons, which is about 8.5% of the global demand. This 6 million ton is mainly used for refining and ammonia. The global demand for hydrogen was 70 million ton on 2020. Why India is betting big on hydrogen? Mainly because of its energy security issues, emission targets, economic dependent and balance on the trade, and energy subsidies. Fluctuation in the oil and gas prices on a daily basis disturb the supply and demand chain, which makes oil prices vary on a daily basis in the fuel stations. And we need to find an alternative to strengthen its national energy security, and hydrogen is important for that. India is the third largest global carbon dioxide emitter, which is about 7% of the emission. Our emission levels are no doubt below China and United States of America. India also has committed to reduce its emission level by 30 to 35% under Paris Agreement by 2030, and by 2070 we have agreed to become a carbon neutral country. India is third largest crude oil importer with import dependence of more than 80%. It also imports 54% of natural gas and 24% of coal requirements, which are greatly affecting our financial balance. India's oil import bill in 2019 and 2020 was approximately US dollar 111.9 billion and US dollar 101.4 billion respectively. India gives overall energy subsidy of approximately US dollar 30 billion per year on oil, gas and coal transmission and distribution, renewable energy and electrical vehicles. Hence, India can grab this early opportunity to capture the entire value chain of hydrogen and look out for global exports. This is one of the main reasons why India is betting big on hydrogen. Decarbonizing targets, complementary solution to renewable energy, supporting grid load management via storage solution, decarbonization of hard to abate sector, technological advancement and falling technology costs are drivers for green hydrogen movement in India. To limit the global warming temperature rise to 1.5 degrees Celsius, large number of renewable energy systems are required to be installed. Hydrogen can be a missing piece to complement renewable energy system to store the excess energy produced during generation hours. Hydrogen-based energy system will help improve the load management also. Hydrogen is a potential fuel and feedstock to reduce carbon intensities of sectors such as transportation, industrial and residential application. There is a significant improvement in the efficiency of electrolyzer and the fuel cell technology in the recent years. Because of these developments, the cost of hydrogen production is going down every now and this price is supposed to go down at a very fast pace in the near future. This is one of the advantage for India, and these are the drivers for green hydrogen movement in India. The global hydrogen market is 100 million tons per annum, and more than 95% of this hydrogen is made from fossil fuels, primarily with natural gas using steam or methane reforming. Hydrogen demand in India can potentially grow more than four-folds between 2020 and 2050, amounting to around 29 million tons. Steel and heavy-duty trucking will be long-term driver for demand in the near future, whereas industrial feedstock like ammonia and refining, increased consumption in these two sectors can require 11 million tons of hydrogen by 2030 from current level of 6 million tons only. As per the Council of Energy, Environment and Water, green hydrogen demand could be up to 1 million tons in India by 2030. Almost 60% of hydrogen demand in 2030 and 94% in 2050 can be made by green hydrogen. The cumulative value of green hydrogen market in India is estimated at $8 billion by 2030 and 340 billion by 2050. Refining and ammonia are two sectors which will foster the demand, whereas steel and heavy-duty vehicle will be more prominent drivers for green hydrogen economy. India can reduce 3.6 gigatons of carbon emission cumulatively between 2020 and 2050. Domestically produced green hydrogen can have an energy import saving of $246 to 358 billion cumulatively between 2020 and 2050. With this, the hydrogen has a very high demand and India is going to be one of the leader. In order to take the lead, IOCL has already started the first green hydrogen plant at Mathura refinery. IOCL is also planning to set up several hydrogen production units on a pilot basis. This includes a project at refinery to produce finite purity hydrogen of 99.9999% for hydrogen fuel cell business. Currently, 50 buses in Delhi are being fueled by hydrogen spike compressed natural gas, which has a 18% hydrogen content. Forecast by various agencies see India fuel demand climbing to 400 to 450 million tons by 2040 as against 250 million tons now. This gives enough opportunity for all forms of energy to coexist. India's total hydrogen demand is expected to touch 11.7 million tons by 2029 or 2030 from current 6.7 million tons. Around 54% of 3.6 million tons of hydrogen is utilized in petroleum refining and the rest in fertilizer production. Reliance and Adani have already announced mega green hydrogen projects to decarbonize their business. This is schematics of hydrogen used for industrial application. We have a renewable energy here. This renewable energy is given to electrolyzer. The water is given as input to the electrolyzer. Hydrogen and oxygen is coming as the output. The oxygen is released into the atmosphere or stored separately. The hydrogen is given to the hydrogen storage tank from where it is going to the fuel cell. The fuel cell produces the energy. This energy is given for the applications or the end user, and the exhaust from the fuel cell, which is water vapor, is going into the atmosphere. The fuel cell also takes the oxygen from atmosphere to burn the oxygen, to burn the hydrogen. In order to take the advantage of the global scenario and demand in India, the government has a mandate to push the green hydrogen generation by 2030. By 2030, the government is planning to generate hydrogen between $1 to 1.5 kg. In order to push the demand, the unlocking of domestic market is also planned. Government is also tapping into green hydrogen export market in a big way, and to encourage the manufacturing of green hydrogen, PLI scheme is already declared to capture $20 billion worth electrolyzer market by 2030. In order to achieve the ambitious targets of green hydrogen in India, we need to focus on the industry, the fertilizer section, the gas economy, the transportation, and the power sector. The industry will include refineries, steel manufacturing, chemical like caustic soda and methanol, industrial heat application, food and beverages. In fertilizer section, urea production, DAP production, ammonium nitrate production, and ammonium phosphate production. In gas economy, we had to blend the hydrogen with natural gas and give it in a grid supply. The compressed gas distribution network also needs to be used for this purpose. In transport sector, the fuel cell electric vehicles, heavy duty and commercial vehicles, trains, aviation and shipping need to be on the hydrogen. In power sector, ammonia seasonal power storage can be one of the area. The generator sets can be converted on the hydrogen, and the gas turbines of hydrogen can be utilized. The existing diesel generators cannot be used for hydrogen fuel, basically because the hydrogen burns very close to the gas cylinder or the IC engine combustion chamber, and it has a 10 times faster flame speed, and the heat generated is more than 500 degrees centigrade. So it requires a complete different engine where the injection timings are different, and it requires a very high efficient thermal management system. There are 5 market segments where green hydrogen can be used immediately in India. Displacement of existing grey hydrogen, feedstock for other high value products like ammonia, methanol and other chemical manufacturing, decarbonization of some current industrial process like steel manufacturing, refineries, cement industry, etc. Blending in existing natural gas system. Blending at 5-10% by volume is possible with minimal modification to existing gas infrastructure, and long-term energy shifting in grid-connected renewable energy systems. Geographies such as Europe and Asia Pacific like India, Japan and China are expected to be a major consumer of green hydrogen. There is very high chance of export of green hydrogen to Japan, Europe and United States of America. In this slide, we can see the green hydrogen and green ammonia value chain. Here we have a renewable energy and water as the input to electrolyzer. The electrolyzer is generating green hydrogen and green oxygen. Green hydrogen is given for ammonia manufacturing, and the green ammonia application is for the fertilizer, for industrial use, for energy storage and seasonal energy resource. Whereas the second application of green hydrogen is for oil refining, heavy duty transportation, steel plants and gas network. Driven by low-cost renewable energy, the country can emerge as one of the most competitive sources for green hydrogen in the world. Disparity in sources and consumption of green hydrogen is bound to create market for green hydrogen as a tradable energy commodity in long run. Energy importers like Japan and South Korea are willing to pay the premium prices and exploring the possibility of importing hydrogen through ocean shipping. European countries are also welcoming prospects from both intra-region and international hydrogen trade. Traditionally, energy exporting regions like Australia and Middle East are increasingly positioning themselves for hydrogen export. Japan and Australia are currently working on a hydrogen energy supply chain project. Green hydrogen from India can be competitive at a marginal for select geographies in 2030, and it will be remarkably competitive by 2050 from countries like Australia and the United States. The requirement of green ammonia and green steel in long run will also act as a big driver for export market of green hydrogen from India. Export of green hydrogen embedded products through an international alliance will also help increase the export, and this confirms or this indicates that there are very high opportunities for export of the green hydrogen to the world, and that's what government is planning to do. Current tariff of solar power generation at 1.99 rupees per kilowatt or approximately 26 cents per kilowatt is there in India, and this power rate is likely to go down further in near future. Saudi also has announced a tariff of renewable power by wind energy at $20 per megawatt hour, and this low tariff of power generation will definitely help minimizing the cost of green hydrogen generation, and in a long run it will help India to manufacture green hydrogen at an attractive price of between 1 and 1.5 US dollar. Electrofuel for ground transportation is also one of the potential applications. E-fuels are primarily hydrogen-based fuels that are produced via hydrogen derived from the water electrolysis of the process. Methanol and ethanol are example of this type of e-fuel. The blending of ethanol and methanol has already started in India, and the blended fuels are available in the market. Government is pushing industry to make the flexible engines where 100% methanol or ethanol can be used, instead of conventional fossil fuel. This will also help in minimizing the emission as the consumption of petrol and diesel will go down. Hydrogen can be also used for cooking and furnace application by blending with natural gas in a limited way to minimize the carbon generation and improve fuel efficiency. Government has already issued guidelines to automobile industry to make the ICE engine flexible to use e-fuels initially by blending and in near future to adopt 100% ethanol. This will definitely boost the hydrogen economy in India. By 2030, 87% of the total hydrogen demand in industrial sector can be met by hydrogen. Hydrogen can be used as a feedstock and fuel for industrial applications. 2% of the hydrogen demand for energy can be supported by hydrogen. It can be utilized as an energy carrier. 9% hydrogen demand for heavy duty transport will be supported by hydrogen. It can be transported as a pressurized gas or a cryogenic fuel and combined with metal hydrides. Whereas 2% demand of the residential and buildings can be supported by hydrogen in the form of fuel cell electric vehicle or mixing with CNG. The total estimated demand of hydrogen is about 20 metric ton with 50% export potential for 2030, and this would require a electrolyzer capacity of 150 gigawatt. In this slide, we can see the entire hydrogen ecosystem. Hydrogen has a great potential to decarbonize hard to abate sector like industry, transportation and building. We are having energy generation from non-renewable sources like solar and wind. This energy is given to electrolyzer where the hydrogen is processed. This hydrogen is given to the industry or it is given to the compressor for compressing, and from here it goes to hydrogen distribution and storage system. It can be a tank or it can be distributed through gas pipeline. It can be distributed through ships and trains and trucks. So these are all the transport means and distribution means for the hydrogen. Now this hydrogen can be used for the end application like fueling the car, fueling the bus, fueling the aeroplane, fueling the industry, or process input for the feedstock, or fuel for heat generation and heat and power generation, etc. etc. In the financial year 2018 and 19, Indian industry consumes 6,688,000 metric tons of gas, the hydrogen gas, 2,600 metric tons for oil refining, 2,850 tons for ammonia, and 752 tons for ammonia transport imported as a fertilizer. This consumption of hydrogen is 2 years ago, which is increased in the last 2 years, and next 2 years again it is going to be increased. Means the requirement is going day by day up, and we will have a very high hydrogen demand. And with the government mandate, the grey hydrogen and the blue hydrogen will be replaced with the green hydrogen. So green hydrogen will have definitely very high demand by 2024 or 2030. In the financial year 2018 and 19, India consumes more than 45 million tons of nitrogen-based fertilizer. The demand for Indian industry in the chemical and refining sector of hydrogen is very high. Oil refineries cover main part of their hydrogen requirement by catalytic reforming, and additional requirements are made by gasification. The chemical industry also requires large amount of hydrogen for production of ammonia and methanol. Hydrogen as an energy vector or chemical agent is also utilized for transportation as a feedstock or heat and power to building and industry. This indicates the demand for hydrogen is going to be very high, and specifically the demand for green hydrogen is going to be very high in the near future. In the financial year of 2018-19, India produced and consumed 5.6 million tons of hydrogen. The transport sector, which accounts for 90% movement of the passenger and 59% of the freight, which generates 88.4% of carbon dioxide emission. India spent $112 billion for import of crude oil. As per the Green Initiative for Future Transport, India is targeting by 2030 1 million hydrogen-powered vehicles on the road, 750,000 hydrogen-powered two and three-wheelers on the road, and 100,000 buses on the road. Hydrogen demand for methanol will increase by 12% CAGR between 2020 and 2050. By 2050, 60% of the hydrogen demand for methanol will be met via green hydrogen. This again indicates that there is going to be very high demand for the green hydrogen in the near future. Niti Aayog has suggested a target of 160 gigawatt of green hydrogen production capacity, out of which 100 gigawatt will be reserved for the export. The potential mandate for the existing applications is also given by Niti Aayog, where the refinery will have a target to convert 50% of its consumption by 2030, and the cutoff date for the sector for 100% green hydrogen utilization will be 2035. The fertilizer sector will have a target to curb the import substitution 100% by 2030 and cut off by 2040. The green hydrogen demand targets will address a demand of 20 gigawatt electrolyzer capacity by 2030 for the local consumption, and the initiative based demand will be about 45 gigawatt. The export demand is considered at 95 gigawatt, making total 100 gigawatt of electrolyzer capacity. And this capacity of electrolyzer to manufacture will open a very big door for local manufacturing also. The cost of green hydrogen depends primarily on the levelized cost of electricity, capital expenditure required, and the utilization factor. Achieving $2 per kg cost of hydrogen production from electrolysis requires an electricity input cost much less than 0.02 kilowatt per hour at existing capex level. With current rupees 1.99 per kWh solar power tariff in India and the new solar parks, the cost of solar power generation is expected to further go down. This will definitely bring down the cost of green hydrogen manufacturing. With low solar power generation, cost of green hydrogen production sub $2 is very well possible in India in near future. Purely based on the cost competitiveness, green hydrogen is expected to dominate the market in the long run. The hydrogen price of 1.99 kilowatt per hour, and which is further likely to go down, achieving a target of less than $2 by 2030 is definitely possible. According to my individual perspective, the cost of green hydrogen generation in India will be drastically low compared to other European countries, mainly due to the low cost of energy and the low labor price. Cost of energy is about 50% in the total cost of hydrogen, and the current solar price at rupees 1.99 per kWh, it requires about rupees 10 energy cost for 1 kg of hydrogen generation. So achieving the lowest cost of production and becoming a global supplier of hydrogen generation, it is very well possible. And government is focusing and targeting the same thing. In order to achieve the targets, government is encouraging and giving full support for manufacturing green hydrogen and equipment required for manufacturing the green hydrogen. Government has announced national green hydrogen policy with a target of manufacturing 5 million tons per annum by 2030. Government is also supporting development of green hydrogen generation and ancillary required for it like renewable power and electrolyzers, etc. For renewable energy generation for green hydrogen, government shall provide land in designated solar parks. The energy transportation for 25 years is free subjected to installations by deadline of June 2025. Producers will be allowed to set up a bunker near the ports for storage of green hydrogen and green ammonia for exports by shipping. The manufacturers of green hydrogen are allowed to purchase renewable power from the power exchange or set up renewable energy capacity themselves or through any other developer anywhere in the country. Manufacturer can bank any surplus renewable energy generated with discoms for 30 days and use it as and when required. India has already committed to achieve net zero carbon emission by 2070. Government is also providing single portal for all clearances required for green hydrogen production. And this is the way the government policies are in the favor of the business, and government is giving support to manufacture the green hydrogen and the equipments required in the country. Government has taken a lot of initiative to boost the green hydrogen production and consumption. In order to build a hydrogen based economy, government has already creating a demand mandate based approach. The right policies for market creation are already there. The progressive and stable regulatory framework is also done. For unlocking the demand, phase-wise scale-up of the system is done. Unlocking the demand in the near future, refinery, ammonia and compressed gas distribution blending will be the first priority. In the next stage, green steel and then the industrial heat applications will be there. In the next stage, heavy duty vehicle and storage is planned. In the last stage, all energy applications will go on the green hydrogen. Stable regulatory framework, policy leadership, and local manufacturing of electrolyzer, green hydrogen, and green refining are going to be the key pillar for success in green hydrogen. Government is pushing green hydrogen demand basically by setting up the target, by demand creation and mandates, and vibrant export market. The target for green hydrogen is 450 gigawatt of renewable energy by 2030. These targets to be based on electrolyzing capacity, cost of hydrogen, delivery, and industry uptakes, etc. The demand creation mandate is by mandating blending of percentage of green hydrogen in the key sectors and greenfield projects to use green hydrogen from future cutoff dates. The vibrant export market will build sectors like green steel for climate-linked exports and secure Asian regional alliances like Singapore, Japan, South Korea for green hydrogen supply. So government is also trying their level best to promote the green hydrogen manufacturing in India. In order to achieve the targets for the green hydrogen consumption, government has targeted the different sectors phase-wise. In the first phase, the focus will be on the rapid gigawatt scale sector like refining and fertilizer. In mid-term, the testing for new applications like city gas distribution, steel, etc. Whereas long-term focus will be on the sectors unlocking like power and heavy-duty trucks. In the short-term focus, refining sector will be targeted with 100% green hydrogen in new urea and refining capacity, blending mandate for old plants in urea and refining, and green ammonia for export. Whereas for ammonia, it will be electrolyzer scale and new capacity by 2030 will be up to 15 gigawatt. Blending of existing stocks will be up to 10 gigawatt and the overall capacity by 2030 will be between 15 to 19 gigawatt. This is definitely a very high capacity and achieving this capacity is not easy. The medium term targets are for testing the new application. The target sectors are gas blending and steel. In gas blending, investing in R&D and pilot project for impact testing and hydrogen blend limits to the existing infrastructure, ecosystem and business model development, designing of equipment for higher blends. The designing of equipment is required because the hydrogen mainly requires very high pressures and the existing gas network is not suitable for that pressure. So it need to be verified. In steel sector, the scales and investment to promote the installations in gas blending, export opportunities, and implement the carbon price or taxes for competitiveness against coal-based technologies. Means the industry who is not going to use the hydrogen will have to pay for higher taxes. The long-term targets are for unlocking the sectors for emerging applications like power and heavy-duty transport. In power, the seasonal energy storage and using hydrogen as gas generator is going to be the main focus area, whereas establishing network for hydrogen refueling station across highways and cities, business model design for hydrogen dispensing, and corridors for long-haul vehicles is going to be a focus area for heavy-duty trucks. Hydrogen can be produced using different technologies, but sustainable production technologies will create a future possibilities of adoption and scale-up. Currently, hydrogen is produced mainly from the fossil fuels such as coal and natural gas. However, it can be generated from various feedstocks also. The most common methods for hydrogen generation are thermal process, electrolytic process, solar driven process, and biological process. In thermal process, a typical high temperature process where steam reacts with hydrogen fuels to produce the hydrogen. Almost 95% of all hydrogen is produced from steam reforming of natural gases. In electrolytic process, water is separated into hydrogen and oxygen through a process called electrolysis. The equipment for converting water into hydrogen and oxygen with electrolysis is called an electrolyzer. In solar-driven process, light is used as an agent for hydrogen production. Some of the processes are photobiological, photoelectrochemical, and solar thermochemical, etc. In biological process, microbes such as bacteria and microalgae and produce hydrogen through biological reaction. Organic matter like biomass and wastewater is used to produce hydrogen in the system. Producing green hydrogen by electrolysis from renewable sources involves breaking down of water molecules into oxygen and hydrogen. In the process, water is used in the electrolysis must contain salt and minerals to conduct the electricity. Two electrodes are immersed in water and connected to a power source, and a direct current is applied to it. The dissociation of hydrogen and oxygen occurs when the electrode attracts ion with an opposite charge to them. During the electrolysis, an oxidation reduction reaction occurs due to effect of the electricity. Electrolysis is a popular process to generate hydrogen. In electrolysis process, electricity splits water molecules into hydrogen and oxygen. An electrolyzer contains two electrodes, an anode and a cathode separated by a membrane and surrounded by the water. Water is put into the system. This water reacts at the anode to form oxygen gas and positively charged hydrogen ions. Hydrogen ion moves across a membrane while electrons flow through the external circuit. Hydrogen ions and electrons meet up at the cathode and combine to form the hydrogen gas with the help of catalyst. So this is a basic process of electrolyzer. Water electrolysis can be done with different technologies like alkaline electrolysis, proton exchange membrane electrolysis, anion exchange membrane electrolysis, and solid oxide electrolysis. In alkaline electrolysis process, potassium hydroxide in water is used, whereas in proton exchange membrane, electrolyte is proton exchange membrane itself. In anion exchange membrane, anion itself is a electrolyte, and in solid oxide, ceramic membranes are used. Alkaline, proton exchange, and anion, all these three technologies are working below 100 degrees centigrade, whereas solid oxide process is working at 800 degrees centigrade. And the solid oxide process generates hydrogen at atmospheric pressure, while the other three generates hydrogen at higher pressure like 30 bar and above. The alkaline electrolysis process is medium flexible while having high efficiency, high maturity, and high market availability. Proton exchange membrane system is highly flexible but having medium high efficiency. The maturity is also medium and market availability is less than 100 megawatt capacity. Whereas anion exchange membrane has a very high flexibility but medium efficiency, low maturity, and it is available only under less than 1 megawatt capacity. The solid oxide membrane has low flexibility, high efficiency, low to medium maturity, and is available for less than 10 megawatt capacity for, and this capacity is not ideally suited for commercial applications. In this slide, we have shown how the different water electrolysis technologies are working and how the oxygen and hydrogen is separated in the process. This is only a graphic representation or schematics, so we'll skip this and go ahead. After understanding the hydrogen market demand, the requirements in India, we understand that there is a very high requirement of hydrogen and the demand is going to go up and up daily. Now, for manufacturing this hydrogen, there are different opportunities like manufacturing electrolyzer, manufacturing fuel cell, scaling up the production, manufacturing hydrogen cylinders, manufacturing storage system for stagnant storage, manufacturing distribution system, and manufacturing dispensing system. The electrolyzer demand in India is likely to be around 31 billion by year 2050, while a demand of 226 gigawatt is expected. India can expect a demand of 20 gigawatt by 2030. Manufacturing opportunities for electrolyzers are very high and between 9 to 12 billion dollar electrolyzers are required in India by 2030 with a potential of 20 to 25 billion. The current capacity of electrolyzer is 10 gigawatt, whereas the global requirement is likely to be 100 gigawatt. Out of this 100 gigawatt, 40 gigawatt will be for European market, 25 gigawatt will be for Chile market, and 5 gigawatt is for UK market. So there is a gap of about 30 gigawatt, and this is the target for India to achieve or to make electrolyzers by 2030. We have seen that there is very high demand of green hydrogen as well as electrolyzers for the green hydrogen. In order to achieve the targets and to fulfill the demand, government has already issued a roadmap for hydrogen business. As per the government roadmap, between 2020 and 2025, green ammonia will be available for exports. Part of the refinery will be switching over to the green green hydrogen. Ammonia for fertilizer will be from green hydrogen, and part of the city gas distribution will be blended with hydrogen. Between 2025 and 2030, the green steel for export will be made out of green hydrogen. By 2030, domestic green steel will be converted on the green hydrogen. Between 2025 and 2030, heavy duty trucking will be converted on the green hydrogen, and by 2040 and 2050, seasonal storage and other energy applications like ships and aeroplanes etc. will be converted on the green hydrogen. Considering the potential required for the electrolyzer for domestic uh, hydrogen manufacturing as well as for export, We already have initiated a project of reverse engineering of electrolyzer with MIT Pune under MNRE scheme to promote the indigenous development and boost the green hydrogen generation. Under the scheme, if the project is approved, MNRE will fund up to 50% of the development cost, and the institution will give us the required support for incubation like space availability, etc. The senior professor who is a doctorate in the petroleum subject will be also available for us. There is a possibility that we can hire the postgraduated student, those who are appearing for the PhD for this project, for which we may have to pay the salaries to them. And once the project is taken over by approved by government, the government will pay those students. We will have to pay some charges for the institution for incubation facility and other support what they will deal. The charges can be negotiated and find out exactly what we need to pay at appropriate time. Now, how are we going to achieve this demand? For achieving the demand, government has already decided that the world's largest green hydrogen generation capacity of over 5 million tons by 2030 will be there for the domestic consumption. The world's largest green steel production at 50 to 20 million tons will be there by 2030. The world's largest electrolyzer manufacturing capacity annually at 28 gigawatt will be operative by 2028 and delivering affordable electrolyzer to local market as well as for the exports. The world's largest green ammonia production for exports will be available by 2030 and it will help other countries to decarbonize. The government is well determined and taking necessary steps to achieve the ambitious targets set for green hydrogen production to be a global leader and exporter. Currently, the electrolyzer market is dominated mainly by alkaline and proton exchange membrane technology. Advanced technologies like solid oxide, anion exchange membrane, and ATAC are nearing commercial deployment by 2024. The stack, power supply, water circulation system accounts for more than 80% of the cost of the PM and alkaline electrolyzers. Power supply alone accounts for about 20 to 30% of the total system cost, and the energy cost is almost 50%. Considering all these technologies, one will have a question that which technology we should go for pilot and small commercial project. So we can go for the proton exchange membrane technology, which is a well matured technology, and the European prospective partner we have contacted has deployed more than 15 systems in the European market. The company is experienced in the hydrogen manufacturing, storage, transportation, dispensing, and applications in various areas like transportation, marine, etc. It means the prospective partner can give us a complete end-to-end solution for hydrogen technology. The company is having its own patented design of the storage tanks, which are based on the carbon composite and one of the lightest tanks available for the hydrogen storage. As an option, we have another technology which is termed as ETAC technology or electrothermally activated catalyst technology, which is developed by a startup in Israel, and this technology will be available for commercial application by 2024. The process will require about 25% less energy as it is not using electrolyzer and it is not using anode and cathodes. Since it is not using anode and cathodes, the cost of the equipment is also likely to go down by about 40% compared to proton exchange membrane electrolyzer. The startup has assured mega-scale equipment for commercial order by 2024, whereas it intends to enter the Indian market by 2025. We already have initiated dialogue with the startup for cooperation for Indian market. Lead time required for 1 megawatt capacity pilot project will be approximately 2 years, whereas a small pilot project of 1.8 kg per hour capacity or 10 kilowatt electrolyzer, the lead time will be approximately 1 year. After manufacturing hydrogen, its storage and distribution is also one of the very important area. The storage of hydrogen has been difficult, basically due to its very low density, very high flammability, and easy of dispersion. Under the normal temperature and pressure, 1 kg of hydrogen occupies a volume of 12.15 meter cube and an energy of 33.5 kilowatt hour. Hydrogen can be stored by three different techniques. First one is a storage of hydrogen in gas form. For storing the hydrogen in a gas form, hydrogen is compressed to 700 bar, and when it is compressed to 700 bar, 1 meter cube of hydrogen will weigh approximately 40 kg. Hydrogen can be stored in liquid form or cryogenic form also. Hydrogen boils at a temperature of minus 253 degree centigrade. So the liquid storage has to be below this temperature. Maintaining this temperature is difficult and it is costly because it requires a lot of energy. The liquid hydrogen weighs approximately 70 kg for 1 meter cube of the volume. Hydrogen can be stored in a solid form also by way of metal hydrides, and the metal hydrides weigh 80 kg per meter cube and above. This slide shows how the hydrogen is stored in compressed or in liquid or in cryogenic form or in metal hydrides. After storage, the important area which needs to be considered is the transportation of hydrogen, because hydrogen needs to be transported to the end application area. This hydrogen can be transported to different places either with the pipelines or using trucks, trailers and ships or using the tanks. Hydrogen can be transported using existing natural gas pipeline or the new pipelines. Hydrogen can be mixed in a fixed proportion for transportation purpose and separated from natural gas on arrival at a destination. Hydrogen storage in a tank is also not a big issue because Inox has recently built and supplied world's largest storage system having a volume of 283 meter cube to South Korea. For mobile transport application like for car and other usage, carbon composite material tanks with a patent technology offers low weight tank for hydrogen storage up to 9 liter volume at 300 bar pressure, weighing only 4.5 kg, and The energy storage is 8.3 kilowatt hour, whereas the lowest volume tank is 2 liter volume with energy storage of 1.9 kilowatt hour. And with this, we can see that the hydrogen transportation and storage is not a major challenge in the consideration. This slide is showing the method of hydrogen storage and how the hydrogen can be stored in a different forms. In this slide, we have discussed the issues related with the different storage technologies. The main issue comes with the compressed hydrogen storage or the gas storage is it requires very high pressure, and this pressure and the system to maintain at that pressure is a challenge. Whereas in liquid hydrogen, the hydrogen boils off at minus 253 degrees centigrade temperature. So you need to maintain a temperature much below this temperature, and it requires a lot of energy to keep the hydrogen cool so that it should not boil off, and it is a costly process. Metal hydrides, although they offer very high density, the capacity of storage is comparatively low, and for extracting the hydrogen, you again need some energy to use. Now we will discuss here the infrastructure required for hydrogen production. Hydrogen production can be done in a two-way. One, by a pilot project rated at 1.8 kg per hour hydrogen generation capacity, or by having a small commercial project rated at 100 kg per hour hydrogen generation capacity. For small pilot project rated at 1.8 kg per hour, the connected power required is 100 kilowatt. The process water required is 18 liter per hour. The building is 100 square meter and open land of 400 square meter is sufficient. Whereas for small commercial project rated at 180 kg per hour hydrogen generation capacity, connected power is 10 megawatt. Process water is 2500 liter per hour. The building is 4000 square meter and open land is 10,000 square meter. The process water can be recycled and reused. So water is not going completely to the waste system. After going through the infrastructure requirement, we move to the capex required for the project. Since the project is proposed on two different structures, one of them is a pilot project which we need to get for reverse engineering also, and the second one is a small commercial project. So we will discuss the requirements for both the projects here. The pilot project rated at 1.8 kg per hour hydrogen will cost approximately 400,000 euro, and while ordering we need to pay 160,000 euro with the confirmed order, whereas the balance payment of 240,000 will be due on invoice after about 11 months, as the lead time required for fabrication is 12 months. This project will also require a solar power generation, and for which it may cost approximately 5,000 US dollar. The hydrogen generation capacity of this project will be 43.2 kg per day, and at a sales revenue of 5 US dollar, it will fetch $216 revenue per day, with expected revenue with expected sales revenue of $78,840 per year and expected payback of 5 years or 61 months. Whereas the small commercial project with a capacity of 180 kg per hour generation would cost approximately 29 million euro, and while ordering the equipment we need to pay 11.6 million euro, and on invoice 17.6 million euro will be payable. This cost is considering project partial fabrication in Europe and partial value addition services in India. The final payment payable will be approximately after 20 to 24 months after ordering the equipment. This equipment will require a solar power generation at a cost of 500,000 dollar. The project will generate hydrogen 4,320 kg on a daily basis, and the sales revenue expected at a $5 per kg rate will be about $21,600, or yearly revenue will be $7,884,000. The payback period will be 3.68 years or approximately 45 months, and lead time requirement is about 24 months. The price consideration here is taken for the grey hydrogen, and green hydrogen will definitely attract higher prices. So this can be a worst case scenario also. After understanding the green hydrogen, the process of manufacturing green hydrogen, the entire green hydrogen economy, and the forecast of green hydrogen in the future requirements, we come to the conclusion that green hydrogen requirements are very high. Now, considering the market potential in India as well as for export of green hydrogen and the government support extended for development of green hydrogen generation, we recommend to go in the business of green hydrogen manufacturing as well as development of electrolyser with MIT World Peace University Pune, because the business of electrolyser is also going to be very huge, and we should exploit this opportunity of going into that business. Now, how do we go ahead with the business? We have already identified the companies, those who are into this business for quite a long time, and we would recommend a joint visit of team to the various supplier prior we choose a potential partner. This visit will give us an opportunity to witness the different technologies, the setup, and the strength of the potential partner. The potential partner whom we have shortlisted as on today is giving us complete end-to-end support, means he is one of the reputed manufacturer in Europe. He already has supplied many hydrogen generation systems to the market. He also manufactures the hydrogen electrolyzer, the hydrogen storage system, the hydrogen transportation system, and the hydrogen application, that is fuel cells. The shortlisted party has its own patented technology for storage of the hydrogen, which is with the carbon composite materials, a lightweight storage system. The potential partner is also supplying fuel cells for various applications like automobile, heavy duty trucking, trains, etc. And we feel that since we will be getting a complete end-to-end solution from one party, it will be most ideal potential partner for us, which we can confirm only after visiting the partner. Now, I would like to give a brief information about myself. I am basically a mechanical engineer, backed up with post graduation in marketing and production management simultaneously. way back in 1980s. I'm having wide experience of over 44 years in the industry, which includes 20 years plus overseas experience. Although basically I'm a mechanical engineer, I'm well familiar with mechanical system, hydraulic system, pneumatic system, electrical system, low tension, power generation and distribution, etc. I was the nominated member of Kenya Bureau of Standard to fix the standards for plastics in Kenya. My last assignment in India was as a managing director cum CEO of Mrs. Berrycap India Private Limited. Berrycap is a group company of MNC having headquarters at Germany. Berrycap is a renowned name worldwide for plastic caps and closures. Berrycap is having 21 manufacturing plants worldwide with 4 in-house R&D centers and 2 in-house tool rooms to develop the tooling. We have successfully implemented over 24 projects on turnkey basis in India, Kenya, Tanzania, Nigeria, South Africa, Kuwait, etc. We have 8 number of design registrations for different applications. We are having very good experience in LT power generation and transmission also. We have successfully implemented a strategic alliance and technology transfer for Pune-based company with European established partner for solar panel manufacturing in India. Currently, we are giving uh, technical support to 2 startups for converting existing petrol rickshaw to electric rickshaw with the same performance like petrol engine. The second project in EV is for 9-meter city bus development. This project is for one of the customer based in Pune currently. However, the base is going to shift to Nagpur very soon.